In this video, we're going to finish up chapter 10, and we're going to look at calculating the rotational inertia or the moment of inertia, and also an introductory look at torque. So first off, if we remember back, what is the moment of inertia? Remember that inertia is the resistance to change in motion when we're talking in the linear sense, while rotational inertia is the resistance in the change in rotational motion. And so it depends upon the object's mass and the distribution of the mass. And so the moment of inertia is defined as the integral of all the distances squared with multiplied by these little infinitesimal masses. And if we integrate all those, we integrate that product, that gives us the rotational inertia or the moment of inertia. And so we can always use this equation in principle. However, in practice, it's very difficult. So we use a set of common shapes and values that we can calculate based on their shape. And so this table kind of summarizes those shapes. And so these are 12 different shapes in their axis of rotation that we'll use, and we know the final end result of the moment of inertia, and we can calculate it. So for instance, a ring or a hoop that's rotating about its center axis, the moment of inertia is just the total mass times the radius of that hoop squared. Now, if we have an inner shell, well, then we have to look at the two different radii, and we can calculate the moment of inertia by using those two different radii. So any shape that's on this list, we can just jump to this formula, and we don't need to integrate. Now, if we know the moment of inertia through the object's center of mass, then there's this parallel axis theorem that tells us if we remove our axis of rotation from the center of mass and we have a known distance h that we remove it, well, we can take the moment of inertia about the center of mass and just add in the total mass times h squared. And so this helps us especially if we're given the moment of inertia of an odd shape and we want to move that axis of rotation. Now keep in mind, I mentioned it earlier, but this is very important. This only works if we're moving from the center of mass axis of rotation. This does not relate the moment of inertia for any two arbitrary axes. So let's look at this example here. We have a book-like sheet of some material. It really doesn't matter what it is, but it's just some object that is a slab. And we want to rotate it about these 4 different axes, and they're all perpendicular to the object. And we want to know which one is going to give us the greatest moment of inertia, or the greatest rotational inertia. And remember, the rotational inertia is dependent upon r squared, and so the greater the distance from the axis of rotation, the greater resistance to change in rotation, or the greater rotational inertia. So obviously 1 is going to be the greatest because that's the farthest away from the mass. And then 2 is going to be the next because it's only at the corner of the mass and we have the most mass away from it as we can. And in 4, we have more mass that is distributed away from it because we're on the edge here. And so then that would leave us with 3 being somewhere in the center or possibly in the exact center. That would give us the least rotational inertia. With these rotational quantities comes our rotational force, which we know of as torque. And so in these next few slides, we're going to look at a few attributes of torque and how we're going to use it in this course. So the force necessary to rotate an object depends upon a couple things. It depends upon the angle and where the force is applied. And so think about opening a door. If you want to open the door, if you apply a force close to the hinge, you're going to get less torque than if you apply it farther away. And if you apply the force at an angle perpendicular to the door, you're going to get the greatest torque, whereas if you're making your angle smaller or closer to parallel with the door, you're going to get less rotation. And so we account for this by using a trig function, and we want to make sure we get the component of the force that is perpendicular to our lever arm, or the distance, the perpendicular distance to the axis of rotation. So the result of that is that the torque is equal to Rf sine theta. R is the lever arm, the distance from the axis of rotation. F is the force. And in this formula, it has phi, theta, phi, whichever angle you want to use. It doesn't matter which Greek letter. And that angle is the angle between the force and the lever arm. Now we use the Greek letter tau to signify torque. Few key terms here are line of action and moment arm. And the line of action is the line in which the force is being exerted, whereas the moment arm is the line of the lever arm, or the perpendicular distance from the line of action to the axis of rotation. And so we use the units Newton meter. Now keep in mind, a Newton times a meter in the linear sense is a joule. However, in torque, it is not a joule. It is not a unit of energy. So we actually say a Newton meter. So don't get torques confused in the fact that, oh, Newton meter is a joule. No, we don't want to call it energy, so we're just calling it a Newton meter. Keep in mind that torque is positive if it would cause a counterclockwise rotation. Otherwise, if it causes a clockwise rotation, it is negative. And if we have many torques acting on an object, we can find a net torque or a resulting torque by summing all of the individual torques. So looking at this example here, we have 4 forces, F1, F2, F3, F4. Actually, we have 5 forces, excuse me, and F5 over here. And the pivot point is located at 20 centimeters from the left edge. And so we want to know, well, which of these forces, looking at all 5 of these forces that are being exerted, rank the forces according to the magnitude of the torque that they produce greatest first. Well, looking at them, they're all relatively the same magnitude of the force. And right away we can say that, okay, 5 is exerting no torque because it's parallel to the lever arm. 2 is exerting no torque because it has a distance of 0 from the pivot point. So that's why those are going to be last. And then we look at, well, it looks like 1 and 3 are the same distance away, and 4 is the same distance away as that, but 4 is at an angle, so that's going to diminish the amount of torque it can apply. So 1 and 3 are the highest, and 4 is next. So if we have rotational force, then we're going to have rotational Newton's laws. And so mainly Newton's second law here, just like in the linear sense, Newton's second law is the sum of the forces equal to mass times acceleration. Well, the sum of the torque is going to equal kind of the mass times acceleration, but in the rotational sense, the moment of inertia times the angular acceleration. And so the net torque acting on an object, we set it equal to I alpha. And then finally here, with force going across a displacement, we are going to have work that's being done and rotational kinetic energy. And we talked about that a little bit in the previous slide, but now we can define it a little better in terms of work. And we know the change in kinetic energy is going to be 1/2 I omega squared, the final angular velocity, minus 1/2 I omega squared, the initial angular velocity. And so this is very similar to 1/2 mv squared, but remember, when we're translating mass into angular, we use moment of inertia, and we're translating velocity into angular, and so we use angular velocity, which is omega. And the work is going to be just like it's the integral of the force with respect to some distance. Well, the work is going to be the integral of the torque with respect to the displacement, which is theta. And if we have a constant torque, then we can reduce this to just torque times delta theta, and that'll give us the work done by that net torque. With work comes power, and power we know is the rate at which work changes, and so the derivative of work with respect to time is the torque times omega. And that's if we have a constant torque or an average torque and an average omega here. This table down below here nicely shows the translation from translational or fixed direction linear motion into rotational fixed axis motion.